Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello, welcome to the episode. I hope you're well and ready to carry on with this topic about entropy and feasibility of chemical reactions. So what we're going to talk about today is actually predicting whether or not a reaction will occur. And to do that, we're going to use a calculation for something called Gibbs free energy. And to do that, you'll need to be aware of the entropy difference between the reactants and the products. In other words, the theoretical entropy change if the reaction were to be able to proceed. And if you haven't yet listened to the previous episode where we talked about entropy and calculating entropy change, then I would suggest going back and listening to that episode now, because without that, it's going to be a bit of a struggle. So pause and go and listen to that if you haven't already, or you need a refresh, and then come back. Okay, welcome back. So we're going to consider something called Gibbs free energy. Gibbs free energy is a factor, a calculated factor that enables us to use that value to predict can a reaction proceed or not proceed under certain conditions. And in that calculation, we will consider the temperature, the entropy change, and the enthalpy change associated with that reaction or theoretical reaction. Don't forget, we can calculate the entropy change and enthalpy change for a reaction on paper, even if it's a reaction that doesn't proceed. So just knowing those values doesn't necessarily mean that the reaction is a reaction that will proceed. When we do the calculation, we'll come up with a value for Gibbs free energy. If that value is negative, it means the reaction is feasible and can proceed. If that value is positive, it means the reaction is not feasible and cannot proceed. So what is that calculation? What is the equation for that calculation? Well, the Gibbs free energy change delta G is equal to the enthalpy change delta H minus the temperature times the entropy change, so T delta S. Let's go through that again. Delta G equals delta H minus T delta S. There's one sticking point that is a common issue here. Enthalpy change is in kilojoules per mole, and our entropy change is given in joules per Kelvin per mole. So we've got a mismatch there. One's referring to kilojoules and one to joules. So when we've calculated the entropy change, or we're given that value, delta S, we need to make sure that we divide by 1,000 to make the units kilojoules per Kelvin per mole, and therefore we've got kilojoules in both terms on that side of the equation. If we don't do that, the calculation is faulty. It doesn't mean anything. Also, don't forget the temperature is going to be in degree Kelvin. So if you are given or have measured the temperature in a different unit, make sure that you convert into Kelvin before doing that calculation. Okay, so when you do this calculation, we're just starting with the enthalpy change and subtracting the temperature times the entropy change, making sure the entropy change is represented in kilojoules per Kelvin per mole. So do that calculation, and if the value you come up with is negative, that means that delta G, the Gibbs free energy change, is negative. That means the reaction may proceed, it's possible, it's feasible. If the delta G, the Gibbs free energy change, is positive, the reaction can't proceed under those conditions. And then there's that situation where the value is 0, and we use that to calculate what temperature is the tipping point on whether a reaction will or won't proceed. So if we consider a reaction, at least a theoretical reaction that might occur, when we calculate the delta H, the enthalpy change, that might be negative or positive. If it's a feasible reaction, they're very often negative, but they can be positive too. So the first term on the right-hand side of the equation is negative, and then we're going to subtract from that T delta S, temperature, times the entropy change. Well, temperature is always going to be positive because it's in Kelvin and there is no temperature below 0 Kelvin. So our temperature, even in extraordinarily cold conditions, is going to be positive. So if our entropy change that we've calculated for this theoretical reaction is negative, then that T delta S term is overall positive. We're subtracting a positive number from a negative number. We're going to end up with a negative delta G overall. If the entropy change is negative, then subtracting T delta S is actually adding a value. And depending on how big that number is, that T delta S number will be, and how big delta H is, we may end up with delta G being greater than 0, meaning a reaction can't proceed. Of course, we can consider the same situation if we have an enthalpy change that says the reaction would be endothermic. We've got a positive delta H. Again, we're starting with a positive number. If delta S is positive, then we're going to be subtracting a positive number. So it depends on the relative size of the delta H and the T delta S terms, whether or not delta G, the Gibbs free energy change, is going to be positive or negative. If we've got positive enthalpy change, delta H, and we've got a negative entropy change, then we're going to start with a positive value and we're going to subtract a negative term. In other words, we're adding T delta S term. We're always going to end up in that situation with a positive enthalpy change and negative entropy change. It's always going to have delta G value of greater than 0, so a reaction can't proceed in that circumstance. Okay, how about the circumstance where delta G is equals 0? How can we use that? Well, we can use that to calculate at what temperature a reaction might occur or not occur. Where delta G equals 0, that must mean that delta H minus T delta S is 0. Therefore, delta H and T delta S terms must be equal to each other. So we know the enthalpy change in theory for a reaction, and we know the entropy change in theory for a reaction. Then in order to make the temperature times the entropy change equal to the enthalpy change, we can calculate what T, the temperature, is in Kelvin. And that temperature is going to be the temperature where the reaction either starts or stops occurring. How do you know if temperatures above T or below T are going to be right? Well, just change the temperature in the calculation slightly one way or the other, and you'll soon see, does that give you a positive delta G, the reaction won't happen, or a negative delta G, the reaction will happen? Okay, so a lot of maths in there, a lot to visualize. So I would recommend going back and listening to this again, and then finding some example questions from your homeworks, from your assignments, from old exam papers, from textbooks, and try it. The math is a lot easier than it sounds in audio if you're actually writing it out. So give it a go. I'd love to hear how that turns out for you. If that's really helped you, that'd be great. If you still have questions and you'd like to do some walkthroughs, like to see it visually, also let me know, please. I'd like to be able to help you. Okay, so that's going to be the end of this topic for this week. I hope that's been useful. If it has, tell a friend, tell your classmates, share it. I'd really appreciate that. Thank you so much. I'll speak to you again soon, and until then, do look after yourself, and goodbye. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistrymadesimple, where you'll be able to ask deeper questions about this topic and get more support for your studies too.